This is the second lecture video for the first day of Math 23B. If you're watching this, it probably means we got so much snow that Harvard shut down. In this video, I'm going to present to you the definition of the Riemann integral in Rn and show you one simple example of how to calculate it, followed by some examples of integrals which don't qualify under this definition, even though they might look perfectly reasonable to you. So we'll start with a bunch of definitions. First definition is the definition of indicator function, which in the previous edition of the book was called the characteristic function. Both terms are standard, and the notation that we're going to use is a bold numeral 1 subscripted by the name of the region for which we have the indicator function, like for example A. And this function is easy as can be to understand. It has the value 1 for any point that's inside the region A, the value 0 for any point that's not in the region A. The advantage of using indicator functions is that we can convert an integral over a possibly rather messy region A into an integral over all of Rn. So if I want to integrate the function f of x over region A, equivalently I can multiply f of x by a function, the indicator function, that is 1 inside A, 0 outside, and then say I'm going to do the integral over all of Rn. These integrals look as though we're doing them over all of Rn, but in fact the indicator function is only going to be non-zero on a bounded region. Putting the dnx in absolute value bars is a bit of Hubbard notation. It's trying to make it crystal clear that the region we're integrating in is the region we're integrating over is not oriented. I will try to write the absolute values whenever I do this. So should you, but there's no real harm in leaving it off. Most other textbooks do. The support of a function is the region in which it's non-zero. So if we have a function that's 2 from x equals 0 to x equals 1, 0 elsewhere, its support is the region from 0 to 1. If the support of a function is not bounded, we can't define a Riemann integral. The supremum of a function, f, on a bounded region A is always going to be denoted by a capital M sort of for maximum, only we're talking supremum rather than maximum. That means even if the region is not closed, we can define the supremum of the function. It's the least upper bound of the function values. As you already know, if the region is closed and bounded, it has a maximum, which is the same as the supremum. Similarly, we denote by little m the smallest value of the function on the region A, its infimum. The infimum is defined as the greatest lower bound of the function values. That way it exists, again, even if the region is not closed. What's going to be very important to us is the difference between the supremum and the infimum. We're going to name that the oscillation and denote it by little osc. Now with those definitions, I can present you with a definition of the Riemann integral in one dimension, which is very similar to what you saw in a previous course, but not exactly the same. So watch carefully. It's the first step that will fool you. We choose an interval a to b, but that's not necessarily just the support of the function or the interval over which we want to evaluate the integral, because a and b have to be integers. So if we have a function that's non-zero only from x equals 2/3 up to x equals pi, the interval that we would choose is a equals 0, b equals 4. That's the smallest region whose boundaries are integers that includes the entire support of that function. The next thing we're going to do is to break each unit length into 2 to the capital N pieces. Each of those pieces will therefore, of course, have length 1 over 2 to the n. This is similar to what you learned how to do in a first course in calculus, except that what we're breaking up is one of these regions that is bounded by integers. This is going to generalize into something we call a dyadic cube. Notice also we only break the region up into 2 or 4 or 8 or 16 or some power of 2 pieces. You're probably accustomed to breaking it into little n equal pieces where little n can have any integer value. Once we've done that, we're ready to go. We evaluate the so-called upper Riemann sum, and the way we do that is for each of these little pieces. These are going to generalize into cubes, so I will denote them by capital C. To get the upper sum, we take the supremum of the function in each of these cubes, multiply that supremum by the length of an interval, 1 over 2 to the n, and then sum over all the pieces. To get the lower Riemann sum, we do almost exactly the same thing, except we use the infimum instead of the supremum. Now, most of the time, as n approaches infinity, u sub n and L sub n will approach the same limit. If they do, then we say the function is Riemann integrable, and you can take the limit of either of them, because both limits are the same. That's the Riemann integral of the function over the chosen region. Let's look at this technique in action. What I want to do is show, using this definition, that the integral of the identity function, f of x equals x, from 0 to 1 is 1/2. You know how to do that using antiderivatives, but we're not using any concept of differential calculus yet. We will need the summation rule, that the sum of the integers from 1 through k inclusive is k times k plus 1 over 2. It's a standard exercise in mathematical induction to prove that rule. So let's start out with our function. There's f of x equals x. My region extends from a equals 0 to b equals 1, and then I start breaking it up. When capital N equals 1, I break it up into 2 little intervals, one from 0 to 1/2, the second from 1/2 to 1. When capital N equals 2, I subdivide each of those intervals and so on. In starting with capital N equals 3, I'll introduce another subdivision point at 1/8. Now, we have to evaluate the upper and lower Riemann sums. Usually you can't do this, but this simple case is an exception. So let's work out the lower sum when the function is f of x equals x and we have 2 to the n subdivisions. First, we have the contribution of the length of one of these intervals. That's 1 over 2 to the nth power. That's a common factor for all the intervals. Then we've got to sum over the infimum of the function in the various integrals. When we are doing the lower sum for capital N equals 2, we have to look at those 4 points, and therefore we are summing from j equals 0 to 2 to the n minus 1, j over 2 to the nth. Notice 2 to the n minus 1 is correct. 3 over 4 is the largest value of the function that we get. Okay, we can evaluate this sum using the rule at the top of the page. We've got a 1 over 2 to the nth outside. We've got another 1 over 2 to the nth from the factor inside the sum. And then we're summing the integers from 1 to 2 to the n minus 1 inclusive. The formula says that sum is 2 to the n minus 1 times that quantity plus 1, 2 to the nth, divided over 2. That cancels that. And we end up with 1/2 times 2 to the n over 2 to the n, which is 1 minus 1 over 2 to the n. In section and on the homework, you will try doing this sort of calculation for slightly more complicated functions like x squared and x cubed. For most functions, there is no way to evaluate these sums. Okay, let's try the same thing with the upper sum. U sub n for the same function f is almost the same. We're summing up values of the form j over 2 to the n, but when we're doing the upper sum, we look at the supremum there, 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 and there, which means j is not starting at 0, it's starting at 1. Our first term is 1 over 4, and it's going all the way up to 2 to the n. So we have as before 1 over 2 to the n times 1 over 2 to the n times 2 to the n. That's k, that's the largest integer in our sum, times k plus 1 over 2. And that nicely simplifies to 1/2 times 1 plus 1 over 2 to the n. Now we look at the difference between the upper sum and the lower sum. This is for a finite value of capital N, so this is just ordinary algebra. If I take this quantity and subtract that quantity from it, the 1/2s cancel out, but I've got 1/2 of 1 over 2 to the n minus 1/2 of minus 1 over 2 to the n. The difference between these two quantities is 1 over 2 to the n. And clearly that approaches 0 as n approaches infinity. That tells us, big surprise, the identity function is Riemann integrable on the interval from 0 to 1. What's the value of the interval? Well, since u sub n and L sub n have exactly the same limit, I can take the limit of either. Let's do it with the lower sum, taking the limit as n approaches infinity of L sub n. Well, no problem doing that. The 1/2 is a constant, and as n goes to infinity, this term goes to 0. So we've got our answer, and we've proved directly from the definition that the Riemann integral of the identity function from 0 to 1 is equal to 1/2. Now, almost no one ever evaluates integrals this way. Even if you're trying to do a numerical approximation to a value of an integral by saying, I'm not going to let n approach infinity, I'm going to use some very large value for n. What you probably want to do is say, I'm going to evaluate at the left endpoint to get a left Riemann sum, or at the right endpoint to get a right Riemann sum, or maybe at the midpoint, or maybe take the average at the two endpoints to get what you may have learned about in a previous course as a trapezoidal Riemann sum. You can take the limit of any of those and you'll always get the right answer if the function is integral, since your quantity that you evaluate for each interval is squeezed in between the infimum and the supremum, and therefore the sum of the quantities that you're looking at is squeezed between the lower Riemann sum and the upper Riemann sum. You can even say, I'll just pick a random point in each interval, evaluate it there. That's a so-called Monte Carlo approach to integration, which turns out to be a very powerful technique when you're evaluating integrals in a large number of dimensions. Now, the great thing about this definition is that we can generalize it to Rn. I will use the term cube generically to represent one of these little subregions. Only when n equals 3 is it what is a cube in common parlance. If n equals 1, it's just a little interval. If n equals 2, it's a square. If n equals 3, it really is a cube. If little n equals 4, you might want to call it a hypercube, and so on. But just as in one dimension the endpoints had to be integers, so here all the endpoints have to be integers. So a valid dyadic cube, that's the term, might have x extending from 0 to 1, y extending from 5 to 6, z extending from -3 to -2. By convention, these cubes include the boundary where the coordinate is smaller, exclude the boundary where the coordinate is larger. So in one dimension, we're talking intervals that are closed at the left end, open at the right end. The textbook is full of problems where you have to show that this convention makes no difference to the value of the integral. I'm going to stay away from these. I will try very hard never to give a problem which relies on your knowing that these intervals are closed at the lower end, open at the upper end. The support of the function, which I denote by a very fancy looking capital D. In Tech, this is MathCal, Cal for calligraphic. If a function has bounded support, this support is going to be contained in a finite union of such cubes. So that's what we do when capital N equals 0. Suppose capital N is positive, like for example, it might be 4. Now our cubes are much smaller. The endpoints have the value some integer over 2 to the capital N in each variable. So for example, x could extend from 0 to 1/16, y from 19/16 to 20/16, and z could be negative, going from -3/16 to -2/16. The volume of such a cube is obtained by taking the length of a side, 1 over 2 to the n, and raising to the little n power. Now we can follow exactly the same procedure. For each level n, we calculate a lower Riemann sum and an upper Riemann sum, and we only have to do the sum over cubes where the function has some non-zero values, where it's not identically 0. If we're lucky, as n approaches infinity, the lower sum and the upper sum will converge to the same limit. If that happens, we say the function is Riemann integrable, and the common limit of the lower sum and the upper sum is the value of the Riemann integral. And as was the case in one dimension, if the Riemann integral exists, then you can do any sort of Riemann sum that you like. You can use any rule for selecting where you're going to evaluate in each cube, and you will get the same answer. This is not quite as great as it sounds. And let me show you why. Here are some integrals that you probably know how to do. Integrate 1 over the square root of x from 0 to 1. Okay, I can do that. Integral from 0 to 1 of x to the negative 1/2 power dx. We have to divide by the exponent of x plus 1. So we got 1 over a half. Raise the exponent by 1. That's the antiderivative of x to the minus 1/2. And we have to evaluate it between the limits 0 and 1. So we get 2 times 1 to the 1/2 minus 0 to the 1/2. And the answer is 2. However, this integral is not well defined as a Riemann integral because as x approaches 0, 1 over the square root of x gets larger and larger and larger. So in this case, the function is not bounded. Therefore, we can't define a supremum in each interval, and this is not a Riemann integral. Another one, integral of e to the minus x from 0 to infinity. Everyone knows how to do that. Take the antiderivative of e to the minus x, which is minus e to the minus x, evaluate it at the limits 0 and infinity, plug in infinity at the upper limit and get 0, plug in 1 at the lower limit and get 1, and the answer is 1. But again, this is not a Riemann integral. What's the problem? The problem is that the function e to the minus x does not have bounded support. It's non-zero no matter how large x becomes. So while the integral of e to the minus x from 0 to a million would be a perfectly well-defined Riemann integral, the integral when we extend the limit of integration to infinity is not. This last one may be a little bit unfamiliar. Consider a function that is 1 if x is a rational number, 0 if x is an irrational number. In that case, no matter how many intervals we choose, and no matter how large a level we choose, the supremum is equal to 1, for the simple reason that any interval, no matter how short, between 0 and 1, contains rational numbers, contains infinitely many of them for that matter. It also contains lots and lots of irrational numbers, so the infimum is 0. And so when we add these up, the upper sum is going to equal 1, the lower sum is going to equal 0, and no limit exists for the difference as n approaches infinity, for the simple reason this difference is 1 for all values of n. The first two examples, the ones you probably met, are called improper integrals. The correct way of doing the first one is to say I can evaluate from some small number epsilon to 1 and then let epsilon approach 0. In the second case, you say I will integrate from 0 up to some very large value, little a, say, and let little a approach infinity. So, these are perfectly good improper integrals, but those improper integrals are not Riemann integrals. The third one you can't do as an improper integral. Let me try to convince you, though, that in some sense the value really should be 0. Suppose we're playing a little game. I say, I'm going to generate a random number between 0 and 1, and all real numbers between 0 and 1 are equally likely. If the number that gets picked happens to be a rational number, you win $1,000. How much would you be willing to pay to play this game? And the correct answer is 0, because the probability that a randomly chosen number between 0 and 1 will be rational is 0. In order to approach this issue more generally, we're first going to have to define the concept of measure 0, and then we're going to have to use that to define the so-called Lebesgue integral. It is very difficult to do probability theory correctly without using Lebesgue integrals. So, for the moment, we know how to calculate Riemann integrals, but they're not going to do the job in every case where we would like an integral. That concludes this part of the lecture.